Welcome to the deep dive. Today we're embarking on a quest really, to uncover the chemical history of our own Milky Way galaxy.
hmm
And what makes this really exciting is that we're armed with some brand new data, the kind that lets us peek into the past with pretty remarkable clarity.
Exactly. Our mission, if you will, is to understand how these meticulous measurements of just one element, cerium, are helping us decode the story of our galaxy's formation.
A story spanning billions of years.
Billions, yeah.
Oh, cerium, atomic number 58. Now that name rare earth element, it sounds scarce, doesn't it?
It does, but it's a bit of a misnomer.
Yeah. Here's a fun fact for you. Cerium is actually more abundant in the Earth's crust than, say, lead or tin.
That always surprises people.
Right. And here's where the galactic detective work kicks in. It has two main isotopes, 140Cs and 142Cs.
And that's key. Because a 140 cerium, that can be made in two different ways in stars. But 142 cerium, only one way, a very specific high-energy process.
Okay, so two different stellar furnaces, basically.
You could think of it like that. We talk about the S process and the R process.
Slow and rapid.
Exactly. The S process is slow neutron capture. This is what makes most of the cerium, and also things like neodymium. It happens mainly in low and intermediate mass stars when they become asymptotic giant branch stars, AGB stars.
Right, near the end of their lives, puffing up.
Precisely. They're gently cooking these heavier elements by slowly capturing neutrons from specific reactions, like carbon-13 reacting with helium.
Okay, and there are variations.
Yeah, there's a Weeks process too in more massive stars, making lighter things like strontium, yttrium, zirconium, uses a different neutron source, neon-22.
Gotcha.
And even a Strong's process in really old metal-poor AGB stars that can get you all the way up to lead.
Wow. Okay, so that's the slow burn. What about the fireworks, the ARP process?
Ah, yes, rapid neutron capture.
Yeah.
Really intense, fast conditions, heavy element creation on overdrive.
And where does that happen? Still a bit fuzzy.
The exact sites are still debated, but the leading candidates are spectacular events like neutron star mergers.
Two incredibly dense things colliding.
Yeah, or maybe a neutron star merging with a black hole. Very extreme environments needed.
So cerium having these two pathways,
Mhm.
process and this R process,
Yeah.
that makes it a good probe, right?
Exactly, because the amount of cerium we see in a star tells us something about the mix of stellar processes that contributed material to the gas cloud that star formed from. It's like a chemical signature.
Pointing back to the source.
And previous studies before the latest data, they sort of showed that the ratio of cerium to iron, Fe, was either flat or maybe decreased slightly as stars got more metal-rich overall.
Metal-rich meaning more heavy elements generally.
Correct. And some work even suggested, that cerium levels might drop for stars up to maybe 8 billion years old and then start climbing again in older stars. A bit complicated.
Okay, which sets the stage perfectly for this game changer. The Gaia third data release, DR3, June 2022.
Gaia,
Yeah.
yes. Just a phenomenal mission. And DR3 gave us this incredibly consistent, detailed analysis of light spectra from millions upon millions of stars.
That consistency is the key, isn't it? Like a standard ruler for starlight.
Absolutely crucial. Gaia's radial velocity spectrometer collected the light, and then a huge effort by the Gaia Data Processing and Analysis Consortium, DPAC, crunched the numbers.
And specifically a tool called GSP spec.
Right. That module within the pipeline took those spectra, those light fingerprints, and worked out the star's properties. Temperature, gravity, and importantly for us, abundances for up to 13 different elements.
Including our friend cerium.
Including cerium, yes, along with zirconium and neodymium, which are also useful traces.
How do they do that? How does Gaia figure out the cerium amount just from light? You can't exactly send a scoop, right?
Ha!
No cosmic scoops involved. It's all about comparison. They compare the observed spectrum of a star, that unique pattern of light intensity at different wavelengths, with a huge library, a grid of pre-computed synthetic spectra.
Computer models of starlight. Exactly. Models showing what the light should look like for stars with different temperatures, surface gravities, and crucially, different amounts of cerium and other elements.
So you find the best match in the library.
And bingo, you get an estimate of the cerium abundance in the real star's atmosphere. It's incredibly sophisticated pattern matching, really.
And the first big analysis of this Gaia cerium data came from Contursi and collaborators in 2022.
That's right. They took the GSP spec results from those 5.5 million or so stars and managed to extract high-quality cerium abundances for about 30,000 of them.
30,000, that's a massive sample and scattered across the galaxy.
Yeah, spread through the disk and the halo, different different galactic components. They even showed a nice example spectrum where you can literally see the dips in the light caused by cerium atoms absorbing specific wavelengths.
Little fingerprints.
Tiny fingerprints. In that example, they measured the cerium to iron ratio, Fe, at 0.26, with some uncertainty, of course. That ratio is the standard way we talk about these things.
Using iron as the benchmark. Makes sense.
It's a common reference. And what's amazing is having this huge uniform data set. It lets you go beyond just individual stars and see the big picture, the large-scale pattern.
So what else did Gaia tell them? Not just the chemistry, right?
Right. They used Gaia's surface gravity measurements, too. That helps figure out what kind of star you're looking at. Turns out most of their sample were red giant branch and asymptotic giant branch stars. Those evolved stars we talked about earlier where the CES process happened.
Ah, okay. Makes sense. They'd be good targets.
And then, crucially, they used Gaia's astrometry, its amazing measurements of star positions, distances, and how they're moving across the sky, their proper motions.
To see if the chemistry links to location and movement.
Precisely. To look for correlations between cerium abundance and where the stars live in the galaxy and how they orbit.
Yeah. Okay, spill the beans. What did they find when they mapped it all out?
Well, a really key finding was about location relative to the galactic plane, the main flat disk of the Milky Way. Stars relatively close by, say within about 1,600 light years above or below that plane, they tend to have lower cerium levels, but they're richer in other heavy elements overall, more metal-rich.
Okay, low cerium, high metals, close to the plane, thin disk stars.
That's the strong suggestion, yeah. Likely residents of the thin disk, the younger, more active part of the galaxy.
And the flip side, stars farther out.
Conversely, stars with higher cerium abundances were generally found to be more metal-poor, so fewer heavy elements overall, and they tend to be located farther away from the sun and farther above or below that galactic plane.
So higher cerium, lower metals, farther out. Sounds like a different population.
Exactly. Two distinct families showing up in the chemistry and location.
And does their movement, their orbits, match this picture?
It does, beautifully. The stars that are more metal-rich and low in cerium, the thin disk candidates, they tend to have nice, orderly, circular orbits around the center of the galaxy, just what you expect for the thin disk.
Right, moving with the flow.
Whereas those higher cerium, metal-poor stars, they're on more eccentric orbits, more elongated, less regular, suggests they probably didn't form in the thin disk.
More like halo stars, maybe? Or thick disk?
Likely candidates for the halo or the related thick disk component, yes. And here's where it gets really cool. They even pinpointed a small group of halo stars with particularly low angular momentum, meaning their orbits are less circular, more plunging.
Okay.
And get this, 11 of these stars matched up with known stellar streams in the halo.
Streams, like trails of stars.
Exactly. Believed to be the leftover debris from smaller dwarf galaxies that the Milky Way tore apart and swallowed up billions of years ago.
Wow, galactic archaeology.
Which streams? They found associations with the Helmi streams, Thamnos, and the Gaia Enceladus stream, also called the Gaia sausage.
So the cerium levels in these stars are tracing remnants of consumed galaxies.
It seems so. It's like finding little chemical clues pointing back to these ancient mergers. And the team also mapped out how the cerium to iron ratio changes generally as you move outwards from the galactic center, and how it changes as you move vertically away from the disk plane. They saw clear gradients.
Okay, so these patterns, these distributions of cerium, they're not just random, right? They mean something bigger.
That's the truly exciting part. They provide really strong independent support for some of the most advanced models we have for how the galaxy actually built itself up chemically over cosmic time.
Ah, the formation models. Okay, tell us about those. How does this cerium data fit in?
Okay, so let's rewind just a bit. Back in 2021, Spitoni and collaborators proposed what's called a two-infall model.
Two infalls of gas.
Right. It was designed to explain patterns seen in another big survey, APG, specifically looking at how alpha elements, things like oxygen, magnesium, compare to iron in stars near the sun. The basic idea was that the stars around us formed from gas that fell into the galaxy in two distinct episodes, two waves. One infall led to stars with high levels of alpha elements relative to iron. The other led to stars with lower alpha levels, like two different chemical recipes for star formation.
Two main batches of material.
Pretty much. But then Gaia DR3 threw a bit of a wrench in the works, didn't it?
You mentioned that earlier, yeah. What was the twist?
Well, when Racio Branco and their team looked at the early Gaia DR3 data, they found evidence for stars that were young but also metal poor and low in those alpha elements.
Young, metal poor, and low alpha.
Exactly. And the original two infall model couldn't quite explain that specific combination easily. It pointed towards maybe needing another piece to the puzzle.
So Spitoni's team went back to the drawing board.
They did. They revisited their model in light of this new Gaia evidence, and in 2022, they proposed a refinement, a 3-infall model.
Okay, 3 waves of gas now. Lay it out for us. What's the timeline?
According to this updated picture, the first big infall, the one responsible for those high alpha stars, happened pretty quickly, over maybe just 0.1 billion years, quite early on.
Fast start.
Then there was a pause. The second major infall, making the first group of low alpha stars, was much more gradual. It took about 4 billion years to unfold, and it didn't even start until about 4 billion years after that first quick infall finished.
Wow. Okay, a long gap, then a slow drizzle.
Kind of. And then another long pause about 11 billion years. After which, the third infall began, maybe around 2.7 billion years ago. This one was quicker again, maybe 0.15 billion years. And it's responsible for that second group of low alpha stars, including those young metal-poor ones Gaia helped uncover.
Goodness, so an initial burst, a long, slow buildup much later, and then another smaller, more recent burst. That's a way more complex history.
Much more intricate than just a single smooth process, yeah. 3 distinct phases of major gas accretion shaping the galaxy's chemistry.
So how does the cerium data, the contorsi analysis we discussed, fit into this 3-infall picture?
This is the punchline, really. The detailed patterns of cerium abundance across the galaxy, where it's high, where it's low, how it relates to metallicity and kinematics is mapped out using Gaia DR3.
Yeah.
It aligns remarkably well with what you'd predict from this 3-infall chemical evolution model.
So the cerium distribution independently confirms the model.
It provides strong supporting evidence, yes.
Mm-hmm.
The fact that measurements of this one specific S-process element tracked across tens of thousands of stars by Gaia fit so neatly into this complex, multi-stage formation history, well, it gives us a lot more confidence.
Confidence in the model and in the Gaia data itself.
Yeah, exactly. It boosts our trust that the astrophysical parameters and abundances coming out of Gaia DR3 are reliable because they're leading us to a consistent picture of galactic evolution that also explains other chemical patterns. 2 different lines of evidence pointing the same way.
Okay, so let's wrap this up. We've taken a deep dive into how Gaia's incredible ability to measure cerium in so many stars is revealing the Milky Way's chemical history. And this isn't just a simple story. The data strongly backs up these sophisticated models where our galaxy grew through multiple distinct episodes of gas falling in over billions of years.
Yeah.
Not one smooth event, but maybe 3 major growth spurts.
Absolutely. And it really is quite amazing when you think about it. We're studying the distribution of one element, cerium.
Seems like such a small detail.
Right. But by tracking that detail meticulously across the vastness of the galaxy, we unlock this fundamental understanding of how this immense structure, our cosmic home, actually came to be.
It really makes you wonder, doesn't it? Gaia measured other elements too. You mentioned zirconium, neodymium.
And others, yes.
How might their distributions further refine this picture? Could they help us pinpoint the timings of these infalls even better? Or maybe reveal even more subtle events in the Milky Way's assembly?
That's the next frontier, exploring all those other chemical dimensions Gaia has opened up.
What other galactic secrets are hiding in starlight, just waiting for us to decode their chemical messages? Something for you to ponder. Thanks for joining us on this deep dive.